Okay, hello everybody. Today we're going to be working through the sample final exam that I put on CourseSite. So let's just start right at the beginning with question one. All right, so for part A, we're just asking to state the limit definition of the derivative. So this is just, do you know it or do you not know it? And the limit definition of the derivative is the limit as h approaches 0 of f of x plus h minus f of x all over h. This is the derivative. And for those here, you're free to talk if you have a question, or you could put in chat if you have a question. Otherwise, I'm just working through the sample exam for the recording. Um, so all part A is asking is just to state the limit definition of the derivative. Uh, so that's that. Then for part B, we want to use this definition to find the derivative of the function given. So let's work through that. So we want to basically plug in this function to this equation. So to do that, first I'm going to figure out what is f of x plus h. Right? F of x plus h is just what we get when we plug x plus h into x. So that's going to be 3 times x plus h minus 2. Just plugging in x plus h for x. Okay, so now that we have f of x plus h, I'm just going to plug in everything into the derivative formula. So I'm going to get the limit as h goes to 0 of 1 over 3 x plus h minus 2 minus just f of x, which is 1 over 3x minus 2. That's all over h. So again, you could try plugging in h here, but I will promise you at this point, it will always be 0 over 0. So we're going to have to do something more here. And that's something more in this case. Doesn't seem like something we could factor. There's no radicals, meaning that conjugation probably won't help us. So that leaves us with finding a common denominator. So let's do that to the top here. Let's find a common denominator. So I'm just going to multiply the first fraction by the bottom of the second, and then I'm going to multiply the second fraction by the bottom of the first. So that's going to leave me with 1 over 3 x plus h minus 2 times 3x minus 2 over 3x minus 2 minus 1 over 3x minus 2 times 3x plus h minus 2 over 3x plus h minus 2. All right, so that if I multiply these fractions, I'm going to get 3x minus 2 over both of these things together. And just so I'm not using too many parentheses, I'm going to distribute this 3. So 3x plus 3h minus 2 times 3x minus 2 minus, over here I have 3x plus 3h minus 2 over the same thing, 3x plus 3h minus 2 times 3x minus 2. And this is all over h. All right, so the whole point of this is now the denominators on top are the same, meaning I could combine these into one big fraction on top. And as the same step, I'm going to say that this h is the same as h over 1. So if I'm dividing by this, I can multiply by its reciprocal. So this is going to be 3x minus 2 minus 3x plus 3h minus 2 divided by the common denominator, times the reciprocal of h, which is 1 over h. All right, we get some cancellation on the top. We have a 3x minus 3x, and we have a -2 minus -2. Those are all going to cancel out. And I'm going to be left with -3h over the h just sort of multiplies on the bottom. So this is going to be h times 3x plus 3h minus 2 times 3x minus 2. The h's then cancel, which is what we always want to happen with these problems. We always want the h's to cancel. That's going to give us -3 over 3x plus 3h minus 2 times 3x plus minus 2. And since I did get the h's to cancel, I know that there's no more to be done calculus-wise, so I could just plug in the limit. So I'm going to say h goes to 0. So this is -3 over 3x plus 0 minus 2 times 3x minus 2. And I'm going to write this as -3 over 3x minus 2 squared. So this is problem 1. Uh,
Professor, do you think you could go over just any problem that talks about the derivatives as rate of change? That was the one problem just on the homework I did not know how to really solve and I was struggling with. So I was hoping you might be able just to go over that type of problem.
of course, of course. So I'll take this a little out of order then. Uh, let's go with right. So number 12 at the other end. Um, so the company that produces wacky wavy inflatable arm flailing tube men operates under this given cost function, where X is the number of units sold and CX is the cost in dollars. And our job here is to just find the marginal cost function and then find the marginal cost at a couple values. So um, the finding the marginal cost isn't too bad. The symbol kind of gives away how we do it. It's just the derivative.
Can I interrupt you for for one
Please, yes,
question?
please do.
Are we gonna have to deal with like the elasticity functions on the exam? Because that was another thing on the homework I didn't really know how to do.
Yeah, it's if you see elasticity, it's going to look like problem 13, which we'll do
Okay.
next.
Okay, thank you.
Um, right. So the marginal cost is just the derivative. So it's going to be d by dx of 45,000 plus 200x plus 10,000 over x. All right, and just to make the derivative a bit easier, I'm going to rewrite the last part here as 10,000 x to the -1 power. So now that I've done this, the derivative is just going to be, well, the first thing is just a constant, so its derivative is 0. The second thing, nothing happens to the 200, and then x, the derivative of x is 1 plus 10,000 times the derivative of this, which is just x to a power, so that's bringing the power out front, times x to the power -1. -1 minus 1 is -2. So this is equal to 200 minus 10,000 over x squared. So this is our marginal cost function. This will tell us that if we're producing X units, the marginal cost is the cost of producing an additional unit. So let's take a look at for part B. We're asked to find the marginal cost when the company produces 10 units. So all that we have to do here is plug in 10 for X. And we get 200 minus 10,000 over 10 squared. Dividing by 10 just cancels a 0, so dividing by 10 squared just cancels two zeros. So we get 200 minus 100, which is just 100. And then finally, part C just is looking at X equals 100. 200 minus 10,000 over 100 squared. Now I'm just canceling out four zeros. So I get 200 minus 1, which is 199. And these should be dollars. I'm sorry, dollars per unit. All right. So assuming we're okay on this, I'm going to move on to the 13, which is deals with elasticity.
Yeah, that's fine.
Okay, perfect. All right. So the economic advisor of a tire store proposes the following demand function. So the demand function meaning that at a given price P, this this function tells me how many we can assume to sell. We could estimate to sell. So the first question that they're asking us is, knowing that both the price and the demand must be positive numbers, uh, to find the domain of the demand function, meaning what are the possible p-values? So what? Well, really, all that we have to keep in mind is what they tell us here is that the price and the demand have to be positive. And I guess looking at this, we also don't want to divide by 0. So I guess three things to look out for. Uh, P is positive, right? So it's greater than or equal to 0, or positive means it is greater than 0. Um, Next, we can't divide by 0. Just looking at this function, I don't want to divide by 0. So that means P is not going to be 40. So 40 is not going to be involved in my domain. And then finally, I need the demand to be positive, meaning that 1800 over P minus 40 is positive. Let's see. The top is always positive. So we need the bottom to be positive. So I want P minus 40 to be bigger than 0, which is the same as saying P is bigger than 40. So the domain is all numbers above 40. So part A answer, the domain is open bracket 40 infinity. And right, it's open bracket because if P equals 40, we're dividing by 0. All right. The next question is just, according to this model, how many tires can be sold in a day at a price of 60? This is just using the function that's given to us, right? Demand tells us the number of tires that are sold in a day at price P. So this is just asking us D of P when P equals 60. And this is going to be 1800 divided by 60 minus 40, which is 1800 over 20. 180 over 2 is 90. So at a price of $60, we can expect to sell 90 units. This is how we use the demand function. Then for part C, we're going to need to find the elasticity function. And the elasticity function is just an equation to know. So see the elasticity, E of P, is given by the derivative of the demand function, ddP, times P over D. And just to rewrite it here, D is equal to 1800 over P minus 40. So let's start by taking the derivative of this. And there's actually two ways we could do the derivative of this. I think I'll do both just for the sake of completeness. So the derivative of this, the first thing we could do is quotient rule. Because we're dealing with a fraction. So the quotient rule says the derivative will be bottom times the derivative of the top minus the top times the derivative of the bottom divided by the bottom squared. And this is equal to, well, the derivative of 1800 is 0. So this is 0 minus 1800, and the derivative of P is just 1 over P minus 40 squared. So we get negative 1800 over P minus 40 squared for our derivative. So that means our elasticity is equal to negative 1800 P minus 40 squared times P over 1800 over P minus 40, like this. And I probably want to get rid of this double fraction. So let me do the same trick where if I'm dividing by a fraction, I multiply it by its reciprocal. So this is negative 1800 divided by P minus 40 squared times P minus 40 over 1800. And I get quite a bit of cancellation here. So let me combine this all together and then we'll start canceling out. So we 1800 P minus 40 divided by 1800 P minus 40 squared. Okay, and the 1800s will cancel, and this P minus 40 will cancel with one of the P minus 40s on bottom, and that leaves you with negative P over P minus 40. And this is the elasticity function. So let's just go over this one more time. Uh, we have the elasticity function given by this formula. The formula requires us to find the derivative of the demand function. So we use quotient rule to find the derivative of the demand function, and we get this negative 1800 over p minus 40 squared. We plug that in for the derivative, and then we have p divided by, we plug in the demand function, and then we just simplify. We just cancel out what they have in common, and this is what we're left with, negative p over p minus 40. Um, As an aside, I did just want to mention that we could have done this derivative by writing this as, or this is equal to 1800 times p minus 40 to the negative 1. And now we could just use the chain rule, right? Because the chain rule tells us that the derivative is going to equal, bring down the power is negative 1800 p minus 40 to the minus 1 is negative 2, multiplied by the derivative of the inside, which is just 1. So we get negative 1800 p minus 40 to the negative 2, which is exactly what we got with the quotient rule. Both of these are valid, whichever one you find easier, you can use. Okay. And then the very last question is, when is the demand elastic? And again, this is a fact that, so elastic means that it's very sensitive to change. And elasticity is the ratio of the change in demand given the price as a percentage. So we want it to be a bigger negative number if it's elastic. Um, Elastic is sensitive to change, and it happens whenever the elasticity is less than negative 1. The elasticity is always going to be a negative number. And if it's less than negative 1, that means the demand is growing, or the demand is shrinking a lot faster than the price is increasing. It's very sensitive to change. If it was equal to negative 1, that would mean that the price is increasing, the demand is increasing at the same rate the price is increasing. So all that I have to do for this is I have to set my inequality equal to, or set my elasticity less than negative 1. P minus 40 less than negative 1. So I'm going to multiply by negative 1 to get rid of the negatives. This means I have to swap the direction. Anytime I multiply by a negative number, I got to swap the direction. So this becomes P over P minus 40 is greater than 1. And this sort of makes sense. If I want negative P over P minus 40 to be less than negative 1, then I want the absolute value to be greater than 1. All right, so from here, I'm just going to multiply by the denominator on both sides. So multiply by P minus 40. So I get P is bigger than P minus 40. And now if I see this, if I see what's going on here, I'm going to subtract by P. And I'm going to get 0 is less than negative 40. Now the question is this a true statement? And the answer is yes. So we have to ask ourselves, it's going to sound a bit weird, but we ask ourselves, for what values of P is 0 bigger than -40? And the answer is all of them. So when the question asks us, for what prices is the demand elastic? Well, it's for every price it could possibly be, which we know from part A is 40 and upwards. So D of P is elastic for P in 40 to infinity. Right? So whenever we're asking if the demand is elastic or inelastic, I just want to set the elasticity less than or greater than -1. And then I want to solve that for P. In this case, we get P canceling out, but that's still fine because we get a true statement. If the less than sign was reversed here, if we saw that 0 was less than -40, then that's always false, meaning that the demand is never elastic. It would be inelastic for P in 40 to infinity. Any questions on this?
Oh, that was good. Thank you.
Of course.
Professor, I know you're posting like the recording. Will you also be posting like the solutions, like the PDF of all the work shown here?
I'll try to. I don't think I could do it directly from here. I might have to rewrite it. So in other words, I wouldn't have it up today, but yes, it will be up eventually.
Okay, thank you.
Of course. Um, okay. And feel free to ask questions at any point, either in chat or in voice, but I am just going to go through the rest of the sample exam then. Unless there are other questions. All right, so limit problems. These should be somewhat familiar. So the first thing we should always try, if able, is direct substitution. As long as we're looking at something that is continuous on its domain, we can try direct substitution. So anything other than absolute values and piecewise functions, we can just try direct substitution. So the limit as x goes to -1, 5x squared plus 1, direct substitution, 6 plus 5 times -1 over -1 squared plus 1. That's 6 minus 5 over 1 plus 1. That is 1/2. If we do direct substitution and we get a real number, we are done. That's all we got to do. For the second one, let's try that again. Let's do limit as x goes to 0 of x over 3 minus square root 9 plus x. Direct substitution gives me a 0 divided by 3 minus root 9. Root 9 is 3. This is 0 over 0. We can never leave our answer as 0 over 0. That's indeterminate. That means there's more work to be done. And looking more carefully, that means that one of three things is true. Either I could factor this, or I could either factor this, or I can find a common denominator, or I could use conjugation. Here, I want to use conjugation because I have a square root, and conjugation helps get rid of square roots. So I'm going to say this is equal to the limit as x goes to 0 of x over 3 minus square root 9 plus x times the conjugate, which is going to be 3 plus square root of 9 plus x. So the top here isn't really going to do anything. So I'm just going to let it carry over. 3 plus square root of 9 plus x. But on the bottom, this is a difference of squares. So this is going to end up being 3 times 3, which is 9. Minus 3 roots plus 3 roots. So those cancel, and I get minus 9 plus x squared, square root squared. So those cancel out and leave me with just 9 plus x. All right, so this is going to be x plus 9 plus x, or 3 plus root 9 plus x over 9 minus 9 cancels, which leaves me with a negative x on the bottom. Now I see there's an x on the top and bottom. I'm going to cancel those out. Limit as x goes to 0 of 3 plus square root 9 plus x over negative 1. I'm going to try direct substitution again, just because now this limit looks nicer, so it might work now. So I'm going to get 3 plus square root of 9 plus 0 divided by negative 1. 3 plus 3 divided by negative 1 is negative 6. And that's my answer. All right. This one is a bit tricky. So if I try direct substitution, x goes to pi of sine cubed x over 1 minus cosine squared x. Try direct substitution here. I'm going to get sine cubed of pi over 1 minus cosine squared of pi. So again, we got to know our pi over 2's of the unit circle. Sine of pi is 0. And cosine of pi is negative 1. So I get 0 over 1 minus 1, which is 0 over 0. Okay. So this means that more work needs to be done. But this doesn't fit neatly into one of our categories of factoring, conjugating, or common denominators. So I am kind of at a loss of what to do here. That is, if I didn't know the most important trig identity. Right, this was on your, I believe it was the second exam. I believe it was the second exam where I had a question where you had to know that sine squared of x plus cosine squared of x equals 1. Well, if this is a true statement, then it's also true that sine squared of x is equal to 1 minus cosine squared of x. Right, I just move the cosine squared to the other side. So that means I could replace the bottom of this fraction with just sine squared. So this is equal to the limit as x goes to pi of sine cubed of x over sine squared of x. And I get cancellation to just the limit of sine of x, or yeah, sine of x, which I could direct substitute sine of pi, which is 0. So yeah, make sure you save some space on your cheat sheet for the trig identities that are important, which I believe, unless I'm mistaken, it was just the sine squared plus cosine squared, and then the pi over 2s of the unit circle was the only trig that I made you remember.
So you basically canceled out the bottom one because, and then you're just left with one sign on top.
Right. Yeah, I have 3 copies of sine on top and 2 on the bottom, so that 2 cancel from the top and bottom. Just like if I had x cubed over x squared. Okay. So these are the normal limits. Then I list some abnormal
Hold
limits
on,
to
could you go
try.
back so I could just
Oh,
get the other?
yeah, of course, sorry.
Thank you. Okay, I got everything. Thanks.
All right, perfect. So these are more abnormal limits. We're going to be dealing with things like infinity and logs. So let's take a look at this. We got the limit as x goes to 4 from the right of x over 4 minus x to the 3. Direct substitution will give me 4 over 0. And since this is a one-sided limit, one-sided limit, a non-zero over 0 gives us plus or minus infinity. So I know my answer is going to be plus or minus infinity, and then I just have to be careful which one to go with. So the limit as x goes to 4 from the right, that means that x is bigger than 4. So if I have 4 minus x, where x is bigger than 4, I'm going to get a negative number out of that, right? Because I'm taking 4 and I'm subtracting something bigger. So this is a negative 0. Then I cube that, it's still negative, and the top is positive. So positive over negative is negative infinity, and that's my answer. Right, so as soon as I do direct substitution without needing to worry about signs, I immediately know my answer is either going to be infinity or negative infinity, because that's just what one-sided limits do whenever you have a non-zero or 0. Then to figure out whether it's positive or negative, we just look at which side we're looking at. So from this side, x is bigger than 4, which means 4 minus x is smaller than 0. So I'm going to be using a negative 0. Now, if this is a negative number in the bottom, cubing it still keeps it negative, and a positive on top isn't going to change it, so it stays negative. If this exponent was an even number, like say this was 4 minus x squared, then it would have changed to a positive 0, because when you square a negative, you get a positive, and we would have gotten positive infinity. For part B, there's an extra layer of complication. So this is our standard limit as x goes to infinity. And we have that rule that basically always works for when the limit goes to infinity. Maybe I'll write the rule just as a reminder that the limit as x goes to infinity oh, right. So if we had ax to the n plus things that are smaller, so this is the largest power, and b over x to the m, we're with a bunch of smaller things, then if n is bigger than m, if we have a bigger power on top than on the bottom, then this thing is going to blow up. We get plus or minus infinity, depending on the constants and the powers, how all those work out. but we're going to get infinity or negative infinity. If n is smaller than m, then I'm going to end up getting infinity on the bottom, which means I go to 0. And if they're equal, well, they kind of stabilize, and thus only the numbers in front really matter. This goes to a over b. Again, I don't mind if you do out the work for this sort of problem, or if you just know this rule that when you're seeing this. But either way, we're going to have to do a little bit of work at least, because for part B, it's not written in this form of just the largest term plus the next largest term plus the next largest. So I'm going to have to factor this at least partially. I actually don't have to do all the work. So whenever I write this out, let me just copy it first. So I know whenever I expand these parentheses, I basically take every choice from the first parentheses and multiply by every choice in the second, right? The first, the outer, the inner, and then the last. So the question is, which of those is going to give me the highest power of x? Well, that's when I take the highest power of x here and multiply that by the highest power of x here. So basically, without foiling, I could basically say this is going to be x squared plus a bunch of things that are smaller than x squared, right? You'll get plus 3x minus 2x minus 6. But again, we're going to infinity, so we don't care about the smaller terms of x. Similarly, the biggest power of x on the bottom is going to be when I take the 3x times the 2x squared. That's going to give me 6x cubed plus smaller things that I don't really care about. Again, there's nothing wrong with doing the whole factor process, the whole foiling, but I'm just saying this is all that's necessary to do because these are going to be the biggest powers of x. And we see that it's smaller on top than on the bottom, so this limit is 0.
So once you factor those out, you just plug in the infinity in for x's for the x's, and that's how you got 0. Because infinity over infinity is equal to 0.
Not quite. So infinity over infinity is indeterminate, but we have this rule over here that if the power on bottom is bigger, then the limit's going to go to 0.
Okay. And but that doesn't apply to just like if the x was equal to infinity, like if it was equal to 1, that would still matter.
Right. If x is equal to 1, then we couldn't do this at all.
Okay.
Um, the way you would do this longhand, by the way, yeah, I'll just do this out. So let's say I take the time to write it all out. We're going to get x cubed plus x minus 6 over 6x cubed plus 2x squared minus 3x minus 1. If you don't want to memorize the shortcut, the method for solving this limit, because infinity over infinity is indeterminate, which means there's more work that needs done. What I would do is I would factor out the highest power of x. Limit as x goes to infinity of x squared times, if I take out x squared, I get 1 plus 1 over x minus 6 over x squared over x cubed, 6 plus 2 over x minus 3 over x squared minus 1 over x cubed. And then in direct substitution, everything that's a number over x as x goes to infinity is 0. So basically, this is equal to the limit as x goes to infinity of x squared times 1 plus 0 minus 0 over x cubed 6 plus 0 minus 0 minus 0. And then I could cancel out an x squared. So this is the limit as x goes to 1 over 6x. Right? If I cancel out x squared, I'm still left with 1 on the bottom. And then this gives me 1 over infinity, which is, again, 0. So this is sort of the long way to do it. Whereas this is the shortcut that we talked about in class. Both are perfectly valid. Okay. All right, next up is another natural log one. The big idea for these natural log problems is to realize that since it's continuous, I could basically ignore it for the purpose of the limit. In other words, the limit as x goes to negative infinity of ln of x to the 9 minus 1 over x to the 9 plus 1. This is equal to the natural log of whatever this limit is. Basically, the limit can pass through natural log because it's a continuous function. So I could solve this one the same way. I'm going to do this the long way again, just for the practice. I'm going to factor out the highest power of x. So I'm going to get x to the 9, 1 minus 1 over x to the 9, over x to the 9, 1 plus 1 over x to the 9. Then the limit as x goes to negative infinity, these 1 over x to the 9s are going to go to 0. So that just leaves me with x to the 9 over x to the 9. Well, anything divided by itself is 1. So this is ln of 1. And ln of 1, we know, is 0. So yeah, just the extra complication of the natural log. And the thing to remember is that limits can pass through natural log. So we could take care of the limit of the inside and then plug that into the natural log to see what happens. All right, so for problem 4, we're on to derivatives. For problem 4, it was mostly just section 3 derivatives, which were power rule and e to the x is a thing. So to evaluate using any method discussed in class, that's just my way of saying you don't have to use the limit definition. Feel free to use the derivative rules. So this is going to be the derivative of 3x to the fourth is going to be 3. The derivative of x to the fourth is 4 times x to the third power. Bring down the power, subtract 1. Minus x cubed becomes 3x squared. We just bring down the power, subtract 1. Plus 14 times 2x to the first power. Minus pi is just the number, so it's a constant. Derivative of x is 1. Plus the derivative of a constant is 0. So this is equal to 3 times 4 is 12x cubed minus 3x squared plus 14 times 2 is 28x minus pi. So that's how you do a derivative with the power rule. And the only difference in the second one is, well, there's two differences. First, we could see that I'm asking for the second derivative here, right? the d squared over dx squared. D over dx means take derivative. D squared over dx squared means take it twice. So for 4b, the first derivative is equal to the derivative of e to the x is just e to the x. Nothing changes with that. Minus 2 times derivative of x cubed is again 3x squared. Minus 5 times 2x plus 3 times 1 minus 0, giving me e to the x minus 6x squared minus 10x plus 3. And then to find the second derivative, I just have to take the derivative of this. So it equals the derivative of e to the x minus 6x squared minus 10x plus 3. And that gives me derivative of e to the x is, again, e to the x. Minus 6 times derivative of x squared is 2x. Minus 10 times 1 plus 0, giving me negative 12x minus 10. And these are the derivative rules that I think are the easiest. The ones that you learn in section 3, the power rule and the fact that exponentials don't matter. And I guess the other rule that we're sort of using without saying it is that you could split it up over sums and differences, and you can move out the constants in front. They don't matter. All right. So for 5, we introduced some of our weirder rules. So the natural log and trig, as well as chain rule. So to handle 5a here, so for handling 5a, what I need to do is, well, I could either think of this as the chain rule, or I could think of this using as the formula for the derivative of natural log. So in the textbook, as I said in class, they give the definition of the derivative of natural log. They say, like, in textbook, they write that the derivative of ln of g of x is equal to g prime of x divided by g of x. And basically all that this is saying is that the derivative of ln of x is 1 over x. And then you add in the chain rule. And that's how you get this formula right here. Right? Because the chain rule says we take the derivative normally, meaning if x goes to 1 over x, g of x goes to 1 over g of x. And then the chain rule says I just have to multiply by the derivative, g prime of x. So let me use this for this problem then. So that means that the derivative of ln 3x squared minus e to the x is equal to, well, on the bottom, I'm going to just get the function, the inside function. And on the top, I get its derivative. So 3 times 2x minus e to the x. So 6x minus e to the x over 3x squared minus e to the x. Whether you do that as the derivative of natural log is 1 over x and then the chain rule, or you just memorize this formula, it gets you full credit either way. Doesn't matter. All right, so for the second one, part B, this is sort of a double composition. We got a function inside of a function inside of a function. Let's see if I could do this without the substitution notation, just to be a bit quicker with it. So we want to take the derivative of sine of e to the 3x. Well, the chain rule says this is just going to be the derivative of the outside function times the derivative of the inside function. So in other words, I look at this sine of e to the 3x and I cover up all this nastiness here. I just look at this as it's the sine of something. The derivative of sine is cosine. So my answer is going to be cosine of whatever this was, but not exactly. The chain rule says that in order to make this completely true, I have to multiply by the derivative of whatever I covered up. All right, so now I need to take this derivative. Well, to take the derivative of e to the 3x, I'm going to do the same thing. I'm going to cover up this 3x, and I'm just going to say that e to the whatever, when I take the derivative, is just itself. And then my tax for making that assumption is I have to multiply by the derivative of whatever I covered up. So I get cosine e to the 3x times e to the 3x times 3. And that is my answer. Then I'm just going to rearrange to make it look prettier. 3 e to the 3x cosine e to the 3x. Like I mentioned when we were learning it, the chain rule is probably the single most important derivative rule that we are going to come across, at least at this level. So it's a very good idea to become comfortable with this concept. Okay. Question 6 is a big one. I ask you a lot of things about a certain function. So let's go through it. We got this rational function, 3x squared minus 12x over x squared minus 16. First of all, we're going to state the domain. As a reminder, how do we find the domain of a function? The domain is all of the x values that we can plug in. And at this level, that means we have to follow 3 rules. 1, can't divide by 0. 2, we can't square root a negative. And 3, we can't take ln unless it's positive. So we have to follow all 3 of these rules in order for x to be in the domain. So looking at this function, there's no natural log, so I can ignore rule 3. And there's no even roots, so I could ignore rule 2. All I need to check for is, am I going to divide by 0? So we divide by 0 when the bottom is equal to 0. Let's see, when does this happen? This happens when x squared is equal to 16. Square root both sides. Remember, I don't just get 4. So x is equal to the absolute value of x is equal to 4. Or as you might be more familiar with saying, x is equal to plus or minus 4. So we get 2 points that are bad. positive and negative 4. So our answer is going to be the domain is negative infinity to negative 4, then negative 4 to 4, then 4 to infinity. Right. Every domain problem works like this. We check our 3 rules, and then we list all the x values that obey these 3 rules. For part B, we're going to find the roots of this function. And finding the roots of this function is legitimately just me testing if you remember what a root of a function is. And we really like roots here. We talk about these things a lot. R is a root of f of x if f of r equals 0. Right? A root is just a number that if I plug it into my function, I get 0. So I find them by setting the function equal to 0. All right, so 3x squared minus 12x divided by x squared minus 16 is equal to 0. Well, the thing is, if I have a fraction a over b equal to 0, it really doesn't matter what b is. A fraction is only 0 if the top of that fraction is 0. Or in other words, you could think I'm going to multiply both sides by x squared minus 16. X squared minus 16. So that's going to give me 3x squared minus 12x is equal to x squared minus 16 times 0 is 0. Now I'll write what's very tempting to do, but I'm gonna actually, there we go. Yeah. I'm gonna write this in red because this is not good. So it's very tempting to look at this and go, okay, add over the 12x. So I get 3x squared equals 12x. Then I could divide by a 3x. So 3x squared over 3x equals 12x over 3x. And that gives me x equals 4. The problem is, one of the rules of algebra is I cannot divide by my variable. Can't divide by x. That's why this is wrong. There is a way you could edit it to think like this and still get the right answer, but I think that just confuses things. So I'm just going to say that anytime I want to divide by x, if I want to divide by x, factor it out instead. So instead of dividing by 3x, I'm going to factor out a 3x. So this gives me 3x is 3x times x minus 4 equals 0. Then one of the rules of algebra, if I have two things multiplied together that give me 0, that means one of these two things has to be 0. So either 3x equals 0 or x minus 4 equals 0. So we get x equals 0 or x equals 4. And that's two roots. So these are both roots. The roots are x equals 0 and x equals 4. These are the two numbers that if I plug it into my function, I'm going to get 0. So again, theoretically, all that we do to find the roots is we set the function equal to 0. From there, it's just algebra. And then just as a algebra reminder, never divide by your variable. If you ever want to divide by your variable, just factor it out instead, and then you'll get this. And it's not like you'll get a wrong answer when you do it this way, you'll just lose answers. Like when I did the red method, I did get that 4 was a root. I would just never know that 0 is also a root by doing this method. That's why it's not a good idea. All right, so we found the domain and we found the roots. Next up, we are going to find the horizontal asymptotes. So remember, y equals a is a horizontal asymptote. I'm going to use lowercase a. If a is a real number and the limit as x goes to either plus or minus infinity of f of x equals a. So if we take a limit as x goes to infinity and we get a real number, that real number is a horizontal asymptote. To save time, and you're more than welcome to do this at yourself on the exam, I am going to do both limits at the same time. So I'm going to take the limit as x goes to both plus or minus infinity. The reason why I'm doing this is because I know that the only time that plus and minus infinity are going to give me different answers is when I'm dealing with piecewise functions or absolute values, or there's one more, square roots. Right. When I'm dealing with roots, absolute values, or piecewise, the two ended limits could be different. But there's none of that in here, so these limits will be the same. And we'll actually see that while we do the problem. So I'm going to factor out an x squared, just like how I do all my limits as x goes to infinity. 3 minus 12 over x. And then x squared, 1 minus 16 over x. I'll cancel out the x squareds. So I get 3 minus 12 over x over 1 minus 16 over x squared, sorry. Not that it makes a difference, but. And the reason why this doesn't matter now is because whether x is positive or negative infinity, this is still going to 0. And famously, positive 0 and negative 0 are kind of the same thing. So we get 3 from our limit. That means that y equals 3 is a horizontal asymptote. Okay. Part D is the same thing but reversed. So for part D, so for a horizontal asymptote, we have an infinite limit equaling a real number. To find a vertical asymptote, we say x equals a is a vertical asymptote if the limit of this real number, so I guess we also need that a is a real number. if either of the one-sided limits, so this plus or minus up on top of the a means either from the left or from the right, the limit of this function is either infinity or negative infinity. We don't need it to show it for both sides. We just need to show it for one side. If either side meaning if we check like the right side and we get infinity, that means we don't have to check the left side. Problem is that there are a lot of numbers and we can't feasibly check them all, but we can narrow it down quite a bit. The only way we could get a vertical asymptote is if we divide by 0. It can only be a vertical asymptote if f of a divides by 0. So in other words, I just need to see my solutions to x squared minus 16 equals 0 give us the possible options. And I'm not going to do the work again. We did that in part A. We get 4 and negative 4. And we got to check both of these. So check a equals 4. I'm going to take the limit. Just pick one of the sides. It really doesn't matter. Limit as x goes to 4 from the right of 3x squared minus 12x over x squared minus 16. For these limits, it is helpful to factor. So I am going to do that. So this is the limit as x goes to 4 from the right of 3x x minus 4 over x minus 4 x plus 4. And I even get cancellation because I'm taking the limit here. So I'm going to get 3x over x plus 4. And then doing direct substitution gives me 12 over 8. Now that's not infinity. So this means I do need to check the other side. X goes 4 from the left. Well, all this work is still the same, so I could just skip ahead and say of f of x is equal to the limit as x goes to 4 from the left of 3x over x plus 4, which is still 12 over 8. So because I get 12 over 8 from both sides, that means that x equals 4 is not a vertical asymptote. Because from neither side did I get infinity. So now I'm going to check the other option, a equals negative 4. So then as x goes to negative 4 from the right of f of x, nothing changed. I could still do all the same work as I did before to get the limit as x goes to negative 4 from the right of 3x over x plus 4. Now here I get 12 over, or negative 12 over 0. And actually what I'm going to do here, we'll come back to this, but what I'm going to say is that this is plus or minus infinity. I don't know which one without testing the polarity of 0, but I know this is enough to say that this is a vertical asymptote. So you can stop here when you're doing this problem, because if it's positive or negative infinity, it doesn't matter. It's still a vertical asymptote. So you don't have to actually find the limit, but just for the sake of doing the problem, getting more experience, let's do that. So x is -4 from the right, meaning x is bigger than -4, which means it's a less negative number than 4. So if I add 4 to it, I'm positive. So x plus 4 is slightly positive. And since it's a positive and a negative, that gives me negative. But again, when finding the vertical asymptote, I really don't care about the sign of infinity. I just care, do I get infinity? So my final answer is x equals -4 is a vertical asymptote. And then finally, for part E, this is the new one. So for part E, we're going to find the derivative. This is just more practice with the quotient rule. So f prime of x is equal to the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. So it's going to be x squared minus 16 times the derivative here is 6x minus 12 minus, let's see here, we get 3x squared minus 12x times 2x. And let's at least collapse all these parentheses on top. So foiling, I'm going to get 6x cubed minus 12x squared minus 6 times 16 is 36 plus 60 is 96 x plus, yeah, things like 16 times 6 and 16 times 12 don't worry about that on an exam. In fact, I'm struggling to do 16 times 12 in my head. I know it's 160 plus 32, which is 192. And this is minus 6x cubed plus 24x squared, all over the same thing on bottom, which gives me the final answer, if I combine like terms, of 12x squared minus 96x plus 192 over x squared plus 3, x squared minus 16 squared. I will accept anything past here on your exam. That's fine. Right. All right, so now we're going to go on to the last 5 problems, I guess, since we already did the actual last 2. So there's 5 more. We want to find the tangent line to the function y equals e to the x plus 1 cosine of x. All right, so equation of the tangent line, we need 2 things. We need a point and we need a slope. We got a point, and then the slope of the tangent line, we should think of that as the derivative. That should be second nature to us, that the derivative is the slope of the tangent line. So the derivative of this function is product rule, right? Because I have e to the x plus 1 times cosine of x. So it's going to be the derivative of one of them times the other plus the derivative of the other times the 1. All right, derivative of e to the x plus 1. The e to the x is just e to the x. And the derivative of cosine is, and derivative of 1 is 0. So it's just e to the x times cosine. Plus the derivative of cosine is negative sine of x times e to the x plus 1. So this gives me e to the x cosine of x minus sine of x e to the x plus 1. So this is the derivative. And then the slope is just the derivative with my x value plugged in, with my point plugged in, basically. So this is e to the 0 cosine of 0 minus sine of 0 e to the 0 plus 1. That's 1. E to the 0 is 1. Cosine of 0 is 1. Sine of 0 is 0. E to the 0 is 1. So it's 1 minus 0 times 2, which is 1 minus 0. So I just get 1. So I have the point 0, 1. I have the slope 1. So y minus 1 equals 1 times x minus 0. Y minus 1 equals x. And that gives me the final answer of y equals x plus 1. This is the equation of the tangent line. Right. All equations of the tangent line problems are the same. You find the derivative. The derivative, when you plug in your point, tells you your slope. You use your point and your slope to make a line. That's not going to change. Okay. For part A, we're finding the derivative of an implicit function. So we have the curve ln xy is equal to x, and I want to find y prime. Find the derivative dy dx or equivalent uy prime. The reason I'm saying this is because when I say the derivative, it doesn't really make sense in a vacuum. I kind of have to tell you what variable we're deriving with. And this is me telling you that that variable is x. So looking at this, I want to see that y is a function of x, and that's what this is telling me. All right, so to find the derivative, to find y prime, I need to take the derivative of both sides. So if I take the derivative of both sides, d by dx ln of xy equals d by dx of x. Well, the right side is easy. The derivative of x is just 1. And on the left side, the derivative natural log of whatever is 1 over that whatever times the derivative of that whatever. Okay. But now how do I take the derivative of this? When I have x times y, I have to use the product rule. So this is 1 over xy times the product rule. So x prime y plus xy prime equals 1. So this is 1 over xy. X prime is just 1, so this is y plus x times y prime, because y prime is just y prime, equals 1. So this is the implicit derivative. Now I just have to solve it for y prime. And there's 3 steps that I could always do to solve this for y prime. I just need to get rid of parentheses, move the y primes to one side, and then factor it in. So let's get rid of parentheses by distributing this 1 over xy. So I get y over xy plus xy prime over xy equals 1. And I could even do simplification here. This is 1 over x plus y prime over y equals 1. Then I want to get all the terms with a y prime onto one side. So I'm going to say 1 over x equals negative y prime over y. And then from here, I just want to get y prime by itself. So I'm going to multiply by negative y to both sides. So I'm going to get that y prime equals negative y over x. And that's my answer. Because for this one, we are just looking for the derivative itself. When we're looking for the derivative, we're just looking for y prime. And again, y prime, dy, dx, they all mean the same thing. And then we're going to do, the next one is the same idea, but now we're applying this to a tangent line. We have a implicit curve, x squared y equals y squared minus 6x, and we want to find the equation of the tangent line at the point 2, 6. Nothing changes here. It's still that the slope is the derivative with this plugged in. It's just now to find the derivative, I need to use implicit differentiation. So it's still the slope. So d by dx of x squared y equals d by dx of y squared minus 6x. So this first term, when I take the derivative, it's the product rule because it's x squared times y. So that's going to be x squared times the derivative of y plus x squared prime times y. This is equal to the derivative of y squared is just 2y. And then whenever I take the derivative of y, I got to use y prime because chain rule. And then the derivative of negative 6x is just negative 6. All right, so this becomes x squared y prime plus 2xy equals 2y y prime minus 6. And if we're solving for the derivative, what we have to do now is move everything with y prime to one side, move everything without it to the other, factor, and then divide to solve for y prime. But since this is a slope question, I don't care about what the derivative is explicitly. So I could actually plug in my point here. So my point is 2, 6. So this becomes 2 squared y prime plus 2 times 2 times 6 equals 2 times 6 y prime minus 6. So 4y prime plus 24 equals 12y prime minus 6. So that means 30 is equal to 8y prime. That means y prime is 30 over 8, which isn't a whole number. I'll write that 15 over 4 just to be a little cleaner. Either way, we have the slope now, 15 over 4, and we have the 0.26, and this is enough to make a line. So y minus 6 equals 15 over 4 x minus 2, which is 15 over 4x minus 15 over 2. Y equals 15 over 4x Moving this over, this is 12x over 2 minus 15x is negative 3x over 2. Or negative 3 over 2. Okay. So again, this is no different than the last tangent line problem. The only thing was to find the actual derivative. It took an extra step. Two more. Number 10, we're going to find the derivative of this function. We're going to find the derivative y equals x squared 3 plus x raised to the power of 1 minus x squared. Here we have a function of x raised to the power of a function of x. The only way we could deal with something like this is logarithmic differentiation. And remember, logarithmic differentiation, this just means apply ln to both sides. Use the log rules. And then just implicitly derive. So if I apply natural log to both sides, I'm going to get ln of y equals ln of x squared 3 plus x to the 1 minus x squared. Well, the first thing I noticed is that there's this multiplication. So the natural log says that that's the same as addition. So it's ln of x squared plus ln of 3 plus x, 1 minus x squared. Then powers in a natural log become multiplication on the outside. So this is 2 ln x plus the power comes out front, 1 minus x squared times natural log of 3 plus x. Okay, so I've used all my log rules. All that's left to do now is take the implicit derivative. So I'm going to apply d by dx to both sides. On the left side, that's just going to be y prime divided by y, because you move the whatever's on the inside, you move it to the bottom, multiply by its derivative. Then this is going to be 2 over x plus, and then here I need the product rule. So this is going to be 1 minus x squared times ln of 3 plus x prime plus 1 minus x squared prime ln 3 plus x. So y prime equals, or y prime over y equals 2 over x plus 1 minus x squared times 3 plus x on the bottom, and then the derivative of this is just 1. Minus 2x, because the derivative here is negative 2x times ln of 3 plus x. And then I just need to solve this for y prime, so I'm just going to multiply over the y. So y prime is equal to y times everything here. So 2 over x plus 1 minus x squared over 3 plus x minus 2x ln of 3 plus x. And I will take this as a final answer, but it is proper to then get rid of this y, because originally at the start of the problem, y is equal to x squared 3 plus x to the power of 1 minus x squared. So it is proper to write this as y prime equals x squared 3 plus x to the 1 minus x squared to all of this. So the only thing that's different between these two steps is I replaced y with the original function. Almost like one of the u substitution examples. And that's how we do logarithmic differentiation. It's just apply log to both sides, use some rules to simplify, and then from there, it's just implicit differentiation. And then we're going to do a hard gear shift to another exam 2 concept of continuity. So we got this function, and I want to find all the points where the function is discontinuous. So when looking at this problem, find all the points where this piecewise function is discontinuous. What I'm basically saying is, for which is this not true, right? F of x is continuous at a. If f of a is equal to the limit as x approaches a of f of x. So for it to be continuous, the limit has to exist, the function value has to exist, and they have to be the same number. Now, for free, we get most numbers already. And all I'm going to say is that algebraic, trig, and exponential functions are continuous on their domains. This is the magic sentence that basically says, I don't have to worry about all of the numbers on the number line, because if I just focus on any of these three functions on their own, they're default continuous. So this means that the only possible discontinuities are at the breaks. So that's x equals 0 and x equals 2. Right? That's when this function breaks from one thing to another. So all that I have to do is I have to just test this formula for a equals 0 and a equals 2. So if I choose a equals 0, f of 0 equals, well, if I plug in 0, that means I am in the middle case. That's when x is greater than or equal to 0. So this is 4 plus sine of pi times 0. And then that's just sine of 0 plus 4, which is 0 plus 4. And then I want to take the limit as x goes to 0. Limit as x goes to 0 of f of x. But since this is a piecewise function, I have to do that by looking at 0 from each side separately. I can't do direct substitution with a piecewise function. So looking at this from the right, so saying x is slightly bigger than 0, that means we're in the middle case. So this is the limit as x goes to 0 from the right of 4 plus sine of pi x. And here, now we could do direct substitution and we get the same thing as before because I'm just plugging in 0 for x. If I look at 0 from the left of f of x, now I'm in the case where x is slightly smaller than 0, and that's 3e to the x. Limit x goes to 0 from the left of 3e to the x. It's 3e to the 0, and e to the 0 is 1, so this is 3 times 1. In order to be continuous, all these three numbers have to match, right? In order for the limit to exist, these two numbers have to match, and then to be continuous, it has to match with this as well. So since 3 is not 4, f of x is discontinuous at 0. Now we got to check the other possible point, a equals 2. Again, I'm going to plug in the function value. F of 2 is equal to, if I plug in 2, I'm in the top case. So that's 4 minus 2 minus 2 is 0. Root 0 is 0. So that's just 4. So it's 2 squared minus root 2 minus 2 is 4. And then the limit as x approaches 2 from the right of f of x. Well, this just means that I'm looking at numbers that are slightly bigger than 2. That is the first case again. And again, I could do direct substitution. It's going to give me the same thing as before. Then limit as x approaches 2 from the left of f of x is equal to the limit as x approaches 2 from the left of, if x is slightly smaller than 2, that puts me in the middle row again. So this is 4 plus sine of pi x. Direct substitute. This is 4 plus sine of 2 pi. Sine of 2 pi is still 0. So this is 4 plus 0, and I get 4. Now these three do match. We get 4 equals 4 equals 4. Which means f of x is continuous at 2. So this question was asking me find all the points where it's discontinuous. We know immediately, since it's a piecewise function, that it could only be discontinuous at 0 or 2. It could be both. It could be neither. And then by checking it, we found that it is continuous at 2, but not at 0. So our final answer is f of x is discontinuous at, or I'll write only at x equals 0. Okay. All right, thank you so much. I will, whoops, I didn't mean to do that. I meant to stop recording.